Okay, for our second set of notes, we're going to do 11-3 notes, and this is on the number e. I think the important thing here to note is that e is not a variable. It is a symbol for a rational number, just like pi is. So pi is 3.14159, blah, 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 blah. E represents the number 2.718, blah, 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 blah. So it's always the same number, just like pi is always 3.14, e is always 2.718. And you actually have that in your calculator, so you shouldn't have to deal with that too much here. And then we have the basic form of the function. And you can see that the basic form, as you're going left to right on the graph, goes up. And that's just the basic e to the x, nothing added, subtracted, multiplied, divide. All right, we're going to jump right to it on the second page. And I managed to not put this on here, and I wanted to. We can just add it right now. And that is, we have a special exponential growth and decay function for the term e, and that is and it looks like this. N equals n sub o times e to the kt exponent. So that's the exponential growth and decay function if we are using e there. So as we read through the problem, it says refer to the application at the beginning. We're not going to worry about that. It says assume that there are 1 times 10 to the 9th kilograms of DDT in the environment in 1973, and that for DDT, K equals 0.0211, and that's just a constant for the function that we're going to find. So the first thing we want to do is write a function to model the amount of DDT remaining in the environment. So that's since 1973. We know that n is equal to n sub 0 times e to the kt. We want to know what n is. N sub 0 is the initial value, and it said the initial value is 1 times 10 to the 9th kilograms. And k, our constant, is negative 0.0211. T is time in years since 1973. So for the first part, we want to fill in our function and represent some kind of model, something that models the amount of DDT remaining in the environment today since 1973. So we're going to fill in our equation and say n equals 1.0 times 10 to the 9th times e. So I want to put that in parentheses. And then the exponent on e is going to be the k, 0.0211 times t. Now t is time since 1973, so what I would do is make t the current year and subtract 1973 from that. So it's going to look a little bit crazy, but there's our function for a. And then for b, we want to say, well, what is it going to be in 2005? So that's where we want to let t equal 2005, and we're going to substitute that into our equation. So it'd be 2005 minus 1973. And you could go ahead and do that if you wanted to. And then you're going to find your resulting value. And the result for B for part B is going to be approximately, if I put it in scientific notation, 5.091 times 10 to the 8th. So part C asks you to graph this function and see what you can verify your answer in part B. So basically you're going to take the function that we came up with in part A and you're going to put it in your graphing calculator, where n is the y and t is going to be your x. And when you graph it, you're going to have something that looks like this. But you've got to be really careful of your range, because the years, remember, that's 2005, so that's going to be on your x-axis. So if we want to look at 2005, that might be right here. And then that intersects then with 5.091, hopefully, times 10 to the 8th. So, you know, we're talking 500 some million on your y-axis. So to be able to see this on your graphing calculator, you would have to change your x and y. Alrighty kids, last one, and we have another fun function for us here. And this is for continuously compounded interest, where it just keeps stacking on the dollars for us, which would be nice if that could happen all the time. So we've got two functions. We've got one that's continuous, which is a equals p times e to the rt, and we've got semi-annually, which doesn't use the t. It's p times 1 plus r over n times n to the t, or nt. So for each one of these, we're going to fill in our equation. We're given that p is 10,000, r is 0.0675, and t is 25. And then when we do the compounded semi-annually, we're going to use n equals 2. So let's do the continuously compounded one first. We want to find A. The principal is $10,000 times e to the, and r is, this is a part of our exponent, 0.0675 times t, which is 25. And if you put all that in your calculator, you're going to get approximately $54,059.49. So you start out with 10,000 and you get 54,000. That's not too bad. Then for the semi-annually, we're going to compare that one. Same principle in rate and time. N is 2, and then the exponent is 2 times, n is 2 times t, which is 25. So that's your exponent, not 2.25, it's 2 times 25. And then when you multiply that out, you should get $52,574.62. So you can see, same amount of money, but compounded continuously is actually going to make you a little bit more. All right, you guys do the worksheets, 11.2 and 11.3, and I will see you on Friday. Bye.